Hi, my name is Daniel. This is Lab 6 Magnetic Molasses. The purpose of lab 6 is to see Faraday's law of induction by watching how a falling magnet induces currents in a conductive tube of aluminum foil. These currents create magnetic forces that oppose the magnet's motion, causing a slower fall. Some models and principles were Faraday's law, Lenz's law, magnetic dipole model, Newton's second and third laws, and the Biot-Savart law. The system was the falling bar magnet, and the induced current surroundings were the Earth's magnetic field, air, environment, and electronics. Our experiment showed that the magnet fell slower through the tube than it would in free fall. The model predicted a time fall of 1.196 seconds, which is faster than the real result. We assumed that the magnet behaved as a magnetic dipole, aluminum tube modeled as independent conductive rings, and the flux only computed along magnetic's axial line. Model predicted that as the magnet falls, the changing flux through each ring induces a current. The induced current should be strongest when the magnet is closest to the ring. Current direction should flip as the magnet passes mid-height. Simulation time was 0.196 and the real was 1.40 seconds. The model underestimated the drag and other factors. Here's some of the equations. These equations show how changing magnetic flux induces a current and how the current creates an upward magnetic force opposing gravity. The simulation updates the magnet's velocity and models its slow fall through the tube. Some measurements, the observations, the magnet fell much slower than the free fall. Motion looks smooth, no bouncing or sticks. Induced currents produce strong magnetic braking. Here's the glow script code. The glow script code simulated a bar magnet falling through a conductive aluminum tube by modeling the foil as stacked current carrying rings and the magnet as a dipole. Here are the calculations. The calculations used the physical measurements of the aluminum tube and the constants from the simulation code to determine the key parameters used in the model. Here's some figures and diagrams. Figure 1 was Faraday's law. 2 is the tube geometry. 3 is forces on the falling magnet. 4 is induced current directions. The figures illustrate the physics behind the experiment and simulation. The diagrams show how it's changing magnetic flux through a ring induces an EMF, which drives current according to Faraday's law. Here's the apparatus and demo. Materials include an aluminum tube, bar magnet, a timer, and a meter stick to measure the tube's dimensions. Photo demonstrates the procedure where the magnet was dropped through the aluminum tube. Some errors that we found was smartphone timing precision was probably not accurate. Aluminum foil was not uniform, causing a difference in the flux. The magnet may have rotated during the fall. Environmental magnetic noise. The experiment successfully demonstrated Faraday's law of induction and the braking effect caused by induced currents opposing a changing magnetic flux. We found that the magnet fall time increased from 30 seconds to 1.40 seconds. Induced currents form clear red and blue regions indicating direction changes. Velocity time curve shape showed a strong upward magnetic force. In conclusion, this lab demonstrated how a changing magnetic flux generates induced currents that create a magnetic force opposing motion.